NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto, a faraway and perplexing smaller planet, was once a singular member of our planetary system's family. However, later disturbing statements by leading astrophysicists, Neil deGrasse Tyson and Michio Kaku, brought Pluto back into the spotlight with a dazzling revelation. They suggest that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a gigantic event? Are we witnessing an intriguing cosmic phenomenon? Or is there more to this looming celestial collision? Join us as we examine the potential outcomes of a Pluto-Neptune crash. Pluto, a former planet that was reclassified as a dwarf planet partly because of its peculiar orbit, remains a subject of interest and study within the astronomical community. According to recent predictions by leading researchers, Pluto's trajectory comes dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku have both raised warnings about a potentially catastrophic collision between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. This means that, since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, measured at 17 degrees to the ecliptic plane. This steep angle sets Pluto apart from the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space focuses on understanding how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like predicting their movements based on their initial positions and how they pull on each other. In Pluto's case, this problem reveals how its path, Neptune's path, and the Sun's gravity all interact in a complex way. Terms like asymptotic libration and resonance libration, along with the VZK oscillation, are key to this puzzle. According to astrophysicists, what keeps all planets in their orbits is a kind of libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from colliding. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of safety from potential impacts. Another crucial factor is the VZK oscillation, named after researchers Vav, Maklev, and Kai, who studied the gravitational interactions of celestial bodies. This oscillation explains how the gravitational pulls of Pluto, Neptune, and the Sun interact. Despite the apparent chaos, this oscillation helps maintain Pluto's orbital stability over incredibly long time scales. The VZK oscillation demonstrates that even though things in space might seem wild and random, specific patterns and rules ensure everything stays in place. These mechanisms help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem also helps us understand how orbits adjust due to gravitational interactions. Studying this provides insights into Pluto, our solar system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is incredibly sensitive, with minor changes in initial conditions leading to significant differences over millions of years. However, these rare properties of Pluto's orbit have been found to maintain stability over unimaginable timescales, effectively containing the chaos. Recent computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune shares a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit. Additionally, Saturn contributes to this stability. These simulations indicate that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for an extraordinarily long time, possibly even billions of years. It appears that Neptune, Jupiter, and Saturn work together to ensure Pluto continues to move safely through space without encountering trouble. These peculiarities are essential in maintaining the order and consistency of celestial bodies. Without these mechanisms, the solar system, as we know it, would be a place of far greater chaos and unpredictability. Bodies like Pluto could collide with others or be ejected from their stable orbits, causing a ripple effect on other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is essential. This provides us with a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continued observation and study of these phenomena to better understand our place in the universe. Delving into the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in the case of Pluto. Even slight variations in Pluto's position or velocity can significantly alter its long-term trajectory. Using virtual simulations, scientists can analyze how slight deviations in Pluto's orbit might impact its long-term trajectory. These simulations also help us understand the intricate balance of gravitational forces within our solar system. Despite its chaotic tendencies, Pluto's orbit demonstrates a surprising level of stability over astronomical timescales. This stability is maintained through the gravitational interplay between the Sun and the giant planets, particularly Neptune, Jupiter, and Saturn. However, questions remain about whether this stability will hold indefinitely. Over billions of years, the cumulative effects of even tiny gravitational interactions could alter Pluto's orbit. This could potentially bring it closer to Neptune, increasing the chances of a collision. Such an event, though highly unlikely in the near future, would have profound consequences for both planets and the broader solar system. A collision between Pluto and Neptune would unleash immense energy, possibly scattering debris across the solar system. This debris could pose a threat to other planets, including Earth, depending on its trajectory. Moreover, the gravitational dynamics of the solar system could be disrupted, potentially affecting the orbits of nearby celestial bodies. Understanding the potential for such catastrophic events underscores the importance of studying celestial mechanics. By analyzing the orbits of Pluto, Neptune, and other bodies in our solar system, scientists can better predict future developments and assess potential risks. Pluto's unique orbital characteristics make it a fascinating subject of study. Its highly inclined and elliptical orbit, combined with its resonance with Neptune, demonstrates the delicate balance of gravitational forces that govern the solar system. This balance allows for stability even amidst apparent chaos, providing insights into the dynamics of other planetary systems beyond our own. While the possibility of a Pluto-Neptune collision may seem alarming, it also highlights the resilience of the solar system. For billions of years, gravitational forces have worked together to maintain order, preventing catastrophic events like planetary collisions. This intricate balance serves as a testament to the complexity and beauty of the cosmos. Looking ahead, continued research and advancements in technology will enable scientists to deepen their understanding of celestial mechanics. By studying the movements of Pluto and other celestial bodies, humanity can gain valuable insights into the forces that shape our universe. Ultimately, the case of Pluto serves as a reminder of the dynamic and ever-evolving nature of the cosmos. It challenges us to explore, to question, and to marvel at the intricate dance of planets, dwarf planets, and other celestial objects as they move through the vast expanse of space. Reenactments has been extraordinarily useful for analysts to sort out how Pluto moves in space. These recreations utilize perplexing math to emulate how Pluto alongside other space objects like Neptune pull on each other by changing little subtleties in the reproductions. Cosmologists can perceive how even minuscule changes can have a major effect in where Pluto winds up in the last part of the 1980s. These recreations showed something truly fascinating about Pluto's circle regardless of having components like asymptotic and scope libration to keep it stable. Its circle can in any case be wild and capricious, assuming that you start with even a little distinction in where Pluto is or the way in which quick it's moving over numerous years. Its way can wind up looking altogether different anyway. Notwithstanding this disorder, Pluto's circle stays stable for quite a while, billions of years. This implies Pluto's excursion around the Sun has a sort of request to it, despite the fact that it appears to be out of control at first. Anticipating enormous occasions, particularly when they include tumultuous circles like Pluto's, presents colossal difficulties. The intrinsic unusualness of these frameworks implies that drawn-out expectations are frequently loaded up with vulnerabilities, while numerical recreations give serious areas of strength for A to comprehend and foresee the future way of behaving of divine bodies. They additionally feature the constraints of our prescient capacities. These models rely vigorously upon the exactness of beginning circumstances and the intricacy of the communications they mimic. Any slight error or twisting can prompt radically various results, making exact forecasts an overwhelming errand. Besides, the turbulent idea of divine circles like Pluto's helps us to remember the consistently developing and dynamic nature of the universe. While we have taken gigantic steps in understanding space, the instance of Pluto helps us to remember how our insight into the universe actually stays restricted. Understanding the gravitational impacts of the Goliath planets on Pluto's circle gives important experiences into the more extensive elements of the planetary group. It demonstrates the way that the presence and position of every planet can have clearing impacts, impacting the dependability and direction of different bodies inside the framework. So for what reason are unmistakable astrophysicists just now raising worries about an expected accident among Pluto and Neptune, in spite of this large number of complicated powers attempting to keep such an occasion from happening? Neil deGrasse Tyson, an eminent astrophysicist, offers an exceptional viewpoint on the secrets of our planetary group, especially the dazzling instance of Pluto. Tyson, known for his job in the renaming of Pluto from a planet to a bantam planet, offers clever discourse on the advancing idea of divine mechanics and the public's interest with the neglected ranges of room. Tyson's situation on Pluto's renaming is established in the always extending information on our planetary group. He considers the renaming to be not a minimization yet, rather a fundamental change in accordance with our developing comprehension of the many bodies circling our Sun. Tyson's way to deal with heavenly mechanics is one of ceaseless learning and transformation. He sees the complexities of Pluto's circle as well as connections with Neptune from a perspective, perceives the unconventionality of room. He proposes that while Pluto's circle is steady for the time being, it could go through huge changes later on. This chance fills in as an indication of the amount we actually need to find about the powers molding our planetary. All in all, Pluto's circle is an entrancing contextual investigation of the mind-boggling transaction of gravitational powers in the planetary group framework. While its way is steady now, the multifaceted elements between Pluto, Neptune, and different planets imply that Even the most apparently stable circles could change over the long haul as astrophysicists like Neil deGrasse Tyson keep on investigating the secrets of the universe. They assist us with better comprehension the fragile equilibrium that administers the developments of divine bodies. The potential for a Pluton-Neptune crash isn't really unavoidable, yet it's a sign of the continually advancing and flighty nature of the universe, notwithstanding the logical hypotheses encompassing Pluto's circle. It's vital to consider the more extensive ramifications of these elements for how we might interpret the planetary group and the universe on the loose. While Pluto's process is one of interest, it's likewise an update that the universe is loaded with stowed-away intricacies ready to be investigated. The idea of orbital reverberation, especially among Pluto and Neptune, is a basic piece of the riddle. This reverberation, where the proportion of Pluto and Neptune's circles is 2 to 3, is a momentous component of heavenly mechanics. For each 2 circles Pluto finishes around the Sun, Neptune finishes 3. This proportion guarantees that despite the fact that the circles cross the 2 planets never impact. This is a result of the gravitational collaborations that balance out their ways, working coupled to forestall any devastating crash. The significance of reverberation in keeping up with vast soundness couldn't possibly be more significant. It gives an illustration of how frameworks in space, even those that at first seem tumultuous, can self-manage through unpretentious gravitational powers. Understanding this reverberation likewise explains why Pluto, in spite of its erratic circle, has stayed stable north of billions of years. This peculiarity is a fundamental part of the planetary group's bigger design. The impacts of planets like Jupiter, Saturn, and even Uranus are critical in keeping up with strength in the circles of more modest bodies like Pluto. Jupiter, with its massive gravitational power, fills in as a sort of defender for the inward nearby planet group, affecting the directions of different space rocks and other bantam planets. Remembering Pluto for truth, a few analysts conjecture that Jupiter's gravity might have kept Pluto from being catapulted from the nearby planet group completely. Without the defensive impact of Jupiter, Pluto's circle could have been upset, undeniably more essentially possibly finishing it out of the Sun's gravitational impact. Furthermore, the idea of gravitational bothers becomes an integral factor over extensive stretches of time. The circles of planets and bantam planets are dependent upon unobtrusive movements because of the gravitational force applied by neighboring particles, while Pluto's circle might appear to be moderately steady now. The places of Neptune and other monster planets can impact its movement, causing little deviations over the long run. These irritations are essential for a more extensive system that drives the advancement of circles all through the planetary group. Space experts utilize modern reenactments to follow these developments, foreseeing how articles like Pluto could develop later on. These models permit researchers to investigate various situations considering different factors, for example, gravitational cooperations and starting orbital circumstances. One more pivotal angle to consider is the job of observational innovation in understanding these peculiarities. The investigation of far-off objects like Pluto has just been potential on account of progressions in adjustable innovation. With the send-off of the new Skyline Central Goal in 2015, mankind had the option to accumulate